very simple, but it's going to be this. And you say that this times this, or you're saying it's going to be A1, A2 plus B1, C2, A1, B2 plus B1, B2, C1, A2 plus B1, C2, C1, B2 plus D1, D2 The proof is very simple. I'm not going to go over that. But I'm going to leave something with you guys. This is, for example, you have two transmission lines. They're in sync. You have one line here. There is a substation here. There is another line here. You know the model for this one. You know the model for that one. If you want to figure out what's happening between this end and that end, just time these two matrices together. You get a new ABCD for the whole system. Now, you guys do this. Go check this out. Again, you have system 1 here. And you have system 2 here. How about these are apart? We'll find the relation between each other. If there are two transmission also like they could be in parallel, right? You can put them in parallel. Just check that out. Tuesday I'll try to solve some examples when we say this program. Today I'm going to continue teaching. Now the next thing is the model for long transmission line. The medium is usually between 80 kilometer to 250 kilometer, and the long transmission line, they are longer than the 250 kilometer. This is we call them long model. But you can use the long model if you want for the short line. It will be more accurate. Because remember, in the short model, we ignored the capacitor, right? We said there is no capacitor. In the medium line, we put all the capacitor in one half here, and one Z here. But in the long model, I'm going to discuss now, we are going to go and say it's not like that. You can put one here, one here, one here. This resistor is going to start from here all the way to here. Every piece of this line has some resistance, right? So that one is a more accurate model. We're going to find the transmission line model with the differential equation for the transmission line model. I'll find out how much is the ABC. At the end, I'm going to come up with the ABCD for the long transmission line model. No question here? Long model. Let's model this transmission line like this. What is this one? Put it on the board. If you remember, we said there is some leakage current. This is the G, they call it conductance. But we didn't talk about it because we said it will be extremely difficult to calculate, right? Because I put it here as a symbol, where we cannot calculate it in this course, but it's there also. This is the capacitance, and this is the resistance, and this is the inductance, or inductance. This is the sending end, this is the receiving end, and this line is a very, very, very long line, right? Longer than 250 kilometers. And when I select a small part of this line, right? A small part of this line. The length of this part is the delta x. And by the way, here is x equal to 0, and here is x equal to f. X equal to 0, x equal to f. Right? To model the line accurate is not like a pi model. You say one y here, one y here, one r here. This r is going to be everywhere in this line, right? This y is going to be everywhere in this line, right? It's not going to be only one place. You say it's in the middle, like a T model, or you say it's end and beginning and end for the pi model, right? The real model is going to be everywhere, right? We can just model it this way. It's very simple. You have like a $100 in your pocket, right? You start to walk from here to there, right? And you start to drop this dollar on the ground, right? So at the end, you don't have any money, So simply you can say, okay, I can go average it out. I said I drop $100 right in the middle, right? Nothing here, nothing there, right? I'll say, okay, in the midway I drop the dollar. Or I can say I put the $50 here, $50 over there. It's like a pi and T model, right? But the reality here, I drop $5 here, $5 here, $5 here, $5 here, all the way over there, right? My point is the model, the accurate transmission line model is like that. You should put the impedance everywhere. It's going to be everywhere, from the beginning to the end, right? Now I'm going to go look at this little part of this transmission line to see how I can use the model here to go find the model for the whole system, right? For this part, I have one y here, one x here. Let's write the equation for this part of the line. Or another example is like driving. You're driving from here to LA, I don't know, for example, to LAX, from here to LAX is almost 120 miles, right? If you drive average 120 miles, you're going to be in there in 1 hour, right? But you're not going to go 120 miles. Sometimes, I'm exaggerating. Let's go that way. If you drive 60 miles, you're going to be there in average. You're going to be there in 2 hours, right? But sometimes there's traffic, maybe you're driving, 5 miles, 6 miles, 10 miles, right? Sometimes there's no traffic, you're going fast, like 100 miles or whatever. You go that fast, right? My point is the speed profile is different from point to point. But usually you can use the average to get a kind of concept of the system. Whatever we have talked about right now is like an average model of the transmission line. Now I'm going to go for piece by piece. What happened here in Lahore? What happened in Delmar? What happened, I don't know, in Colbert? What was my speed? I'm going to go piece by piece, getting more detail. How much is the voltage drop? How much is how I can model it? Now So we start to do the same equation here. I can write a KVL here, I can write a KCL. Let's start with that. See, so just the notation. Let's just go with the notation. See, this is the x. This coordination is x, right? I call it this point, I call the voltage Vx, and the current I call it Ix at this coordination. I went delta x away from here. At this point, I call it Vx plus delta x. The position is x plus delta x. The current also is going to be x plus delta x. They're not going to be the same, right? Now let's write the equation. How much would it be x plus delta x? It's going to be basically this times Ix, right? It's going to be z delta x. And look at it here. Delta x is length of this one. Delta x is length of this transmission line is selected. We can go select like a 1 meter. We can say, okay, I have a 250 kilometer of the transmission line. It's based on how accurate you want to be. You can say I want to select delta x would be 1 centimeter. 250 kilometers divided by 1 centimeter, I don't know what it is. It's going to be maybe 2.5, I don't know, billion elements. You know what I'm saying? You're going to have 2.5 billion of these models attached together. Like here, see? Look at here. I'm going to have if I make it 1 centimeter, I can come up with a kind of simple model for it, right? I can put it 2.5 billion of this one in series, right? And time all together to get the model. But that would be really difficult to calculate, that kind of thing. But now, voltage at this point is equal to this current times this impedance plus Vx, right? This one, Vx. Let's put this one here divided by delta x. So it's going to be Vx plus delta x minus Vx over delta x is going to be Zix, right? It's going to be Zix. What is this? Just remember a little bit of calculus. What is that? dV over dx, right? It's the dV over dx. Right? We got this equation. Actually, yeah. dvx over dx. Now let's go for the KCL. I'm going to write a KCL here. I'm going to write a KCL here. This is one equation. Ix plus delta x is equal. How much is the current here? This times this voltage, right? Is going to be y delta x times Vx plus delta x, right? Plus Ix. So sorry. Let's again do this one. Ix plus delta x minus Ix over delta x is going to be what? It's going to be y Vx plus Vx plus delta x. Right? It's going to be that. What is this? So this one is a di over dx. Dix over dx is going to be 1 basically bend delta x goes toward dx. Think about it. Delta x is going dx, means it's very small, right? Very small. I can say dx plus delta x is going to be what? Dx, right? So basically it's going to be y. If I make this length, think about it, just physical. Now that one was the math we talked about. We said, okay, I'm gonna move the delta x toward dx very small. So mathematically means that there is no distance. Well, look at here, physically, look at it. I'm gonna make this distance small and small and small and small. So it basically the difference between this voltage and this voltage is gonna get less and less, right? If I have 1 millimeter of line and I have 10 millimeter of line, so the voltages are much closer for 1 millimeter, right? If I'm going to go, I don't know, thousandth of the millimeter, it's going to be the voltages are going to be much closer, right? So that's very simple. Basically, the drop voltage is getting smaller. When I reduce the length of the line, the drop voltage is going to get smaller. So basically, beginning and the end almost become the same voltage, right? Vx plus delta x is equal to dx. So two equations. I'm going to go replace this one here. 1 into 2. So before doing that, because we have it. So let's take another derivative of this one. It's going to be d2dx over dx2 is going to be z dix over dx, right? I take a derivative from both sides, right? Now I'm going to replace dix over x dx from there. So it's going to be d2 dx over dx2 is equal to z times y dx, right? So basically it's going to be d2 dx over dx2 minus zy dx, right? This is a differential equation of this partial of the line, this part of the line. This is very simple to solve it, right? You know what's the answer for this one? Can you remember from you have this one last understood before you have this one. But that's very simple to solve it, right? You have a, I don't know what you call it, axillary equation, something like that. Say S2 minus zy equals to 0. So basically S is going to be a square root of zy, right? And now plus minus square. Plus minus zy. Right? So let's write the answer. You don't need to be worried about this proof, but you know, we're going through that. We're going to get the model, parameter model, and that's it. That's where we're going to end up for the transmission line, long transmission line. Now, I'm going to write the Vx. Vx is going to be Vx is going to be A1 is the second order equation. It's going to be A1, right? A1 e to the power of the answers we have over there. S. So basically it's going to be, I think you call it gamma. This group, you call it gamma, let me make sure. Gamma. I call it gamma. So we call it gamma x plus A2 e to the power of minus gamma x. And gamma is equal to zy. gamma is the square root of V1. And the unit for the gamma is 1 over meter. Yes, 1 over the unit for this one is 1 over meter. Because the unit for Z is ohm per meter. The unit for Y is Siemens per meter, right? Ohm times Siemens is going to be 1, right? We're going to have 1 over meter to the power of 2. The square root of that is going to be 1 over meter. The unit for gamma is 1 over meter. Now, we need to calculate this A1 and A2 to see how much are these values. Before going there, let's calculate I first to see how much is I. We want to calculate the I to see how much is I value. Let's calculate I. I have the dI over dx equal to this one, and I have the dx equals to that one. I can find how much is the di over dx. Take the integral of that one, I can find how much is I, right? Let's first find out how much is the dv over dx. dv. Yeah, okay, sorry, from here. We use it from here. We can use it from here. Let's calculate dv over dx. So it's going to be A1 gamma e to the power of gamma x, right? I think it's not about x. A2 gamma e to the power of minus gamma x, I believe. And we know from equation 1, so I think I call it equation 1. Equation 1 it says dv over dx is equal to z ix. Right? So basically, Ix is going to be A1 over Z, A1 gamma, over Z to the power of gamma x minus A2 gamma over Z to the power of minus gamma. So now we have the Vx and we have the Ix. I need to find out how much is the A1 and A2. I need to figure out those values and we are done. Right? Let's go for those. So the initial at this point, how much is the Vx at this point? Is the VR. How much is the Is? Is IR, right? So let's put it here. X equal to 0, so V0 is how much? VR, right? And I0 is how much? IR. Now put it in these two equations. If I put it here, 0, I'm going to put for x 0. How much is this one? E to the power of 0 is 1. E to the power of 0 again is 1. So basically A1 plus A2 is going to be VR. Right? Now let's put it in this equation. Again, this one is going to be 1, right? This one is going to be 1 again, right? So basically, A1 gamma over Z minus A2 gamma over Z is going to be how much? I. So you can go, I'm not going to go through this detail anymore, you know what happened, you have to calculate this thing. So you can go calculate A1 and A2. If you can calculate A1 and A2, you know, let me write it here. So if you calculate A1 and A2, that's when you put the final answer here. A1 is going to be VR plus ZC IR over 2, and A2 is going to be VR minus ZC, I'll tell you what's ZC, IR over 2. and ZC is they call it surge impedance. ZC is Z over 1. And the unit is this. So now we have A1, A2. Basically, see if I replace this one here, look at here. If I replace A1 and A2 here, I have the voltage for any point, right? And if I replace them here, I'm going to have Ix for any point, right? But what do I want? So basically Vx is going to be Vr plus VCIR over 2 e to the power of gamma x plus Vr minus VCIR over 2 and e to the power of minus gamma x, and the Vix the same thing, right? But different path, right? I'm going to stop here, and but before finishing here, just like I said, what I did here. Next, what I'm going to do, I'm going to separate them. For example, I say Vr over 2 e to the power of gamma x, Vr over 2 e to the minus of gamma x, right? I'm going to factor in V, so it's going to be basically Vr is going to be something, sorry, Vx is going to be something times Vr plus something times IR, right? The same thing here, it's going to be something times Vr plus something times IR, right? I'll go through these somethings, Friday, Saturday. Now, the last thing, if you know this something, this is what I put it dot. I want to find the relation between the Vs and Vr, and Is and IR, right? If I put X equal to L, if X is equal to L, how much is the Vx? Is the Vs, right? And how much is the IL? Is Is, right? So basically in this equation, I'll put X equal to L. So this one is the Vs is equal to something times Vr, something times IR. And Is is equal to something times Vr. This something they're going to be ABC. We're going to ABC of the transition. We'll go over it, we'll complete this one Friday. Saturday. So we came up to here, I'll repeat this one, Saturday class. To get the ABC and finish this model. So she will send you an email tomorrow to let you know where is the class and what is the exact time you're going to start. The class is only 2 hours. So whenever you start 2 hours after that,
I had it already this week.